We're going to talk about techniques in this class using DFTs in which span the gamut from letting you understand how probability works to letting you see how to multiply numbers back in fourth grade, doing long multiplication. You're going to see all kinds of amazing applications, including cryptography. The best attempts to break our most cryptographically secure codes right now are based in the questions of zero pattern. So there's a lot of neat stuff coming up about that. But for now, we got to get the time domain stuff down. And sampling is the way that we move from continuous time to discrete time. So just as an example, say you've got a signal that looks like this. Because everything we do in this course, the whole purpose of digital signal processing is to get things done by computers. Unless I make it abundantly clear we're talking about signals that start off at negative times, all of our signals we're going to assume start at time equals 0. So here's a continuous time signal. And I've lost the ability to count. And here's a few samples. Here's our horizontal axis. So when you sample this, you sample at a particular time, t sub s for your sampling time period. And let's say you want to sample it at t sub s equals 1. So now you've changed that continuous time signal into this, into these three numbers. 0, 1, 2, 3. What would happen if instead you sampled it at t sub s equals 1/2 second? Your numbers, as you're counting them, stay the same distance apart. They're still separated by ones, but now you're going to be sampling it not just here, but also here. And so now it makes it look like your signal is decaying far more slowly. And if you were to continue sampling at a faster and faster frequency, your signal would eventually even out, and eventually it'd look like it was unchanging. You'd zoom in so closely that over the period of several indices changed, you won't see a difference in your signal at all. So faster sampling stretches your signal more. You get more detail. Or you zoom in.
And that's the basis of derivatives, right, sir? About like sampling at a faster rate?
No. Derivatives have to do with we'll talk about that soon too. These are great questions. You're a good class. Derivatives have to do with a unit sample with a h of t that looks like, with an h of n, that looks like this. And that should not be at all obvious what we're talking about now. Still separated by exactly 1 and 0 everywhere else. And we'll get into what that is shortly. Tell me what you meant by derivatives.
I meant
and stretching.
the way that I was picturing derivatives was just how you cut down instead in that same time period you went from 1 second to half a second, and it's kind of like the unit length of time. That's what I meant by shortening it each time.
I understand. So you're saying that the derivative is a limiting argument. It's the limit as delta goes to 0 of f of x minus let's do it in the positive direction, easier, of x plus delta minus f of x over delta, and that's the derivative. It's like that, except that in the derivative we're modifying it by dividing it by 1 over delta. So yes, the numerator is like a derivative, but when you're taking a derivative, multiplying by 1 over delta has the effect of making these things bigger and bigger. And eventually, you end up with a impulse response, h of t, that looks like a impulse pointing straight up here and an impulse pointing straight down here. And that's called a doublet. It's the derivative of an impulse. And you're right, that is definitely related to this, but at a graduate school level. There's some beautiful theory that goes into it. And as we go through this course, you're going to see a connection between discrete time algebra and calculus in many different ways. So yeah, I agree that the numerator does have to do with, is similar to sampling.